It's great to be here to talk about some of my research. So, as Scott was explaining, I consider myself sort of a comparative planetologist. So I look at trying to understand the similarities and differences between rocky worlds, both inside the solar system and outside the solar system, and try to leverage the new population of planets we're discovering outside the solar system to better understand the evolution of planets in our system over time, because these exoplanets occupy many ages, many different parameter spaces than the rocky planets in our own solar system. So specifically, my research group really focuses on understanding the formation and evolution of the atmospheres of these planets and the role of both internal and external forcers on those evolutionary processes. Things like the stellar radiation the planet is receiving or impacts from asteroids and how that modifies the chemistry of those atmospheres, especially early on. And then understanding how the atmospheres and the oceans of those objects interact with the planet interior and surface over time through the process of tectonics and volcanism, and how that shapes the habitability of the surfaces of these planets. So what I want to tell you about today is thinking a little bit about the population of exoplanets that have been discovered in the last 30-odd years. And how those provided really an opportunity in order to better understand our own solar system. So here's our solar system. The planets here are to scale with each other and sort of looking at actual images of the planets rather than sometimes we get cartoony images here. And just to give you the lay of the land for our solar system, in the inner system closest to the sun we have the rocky planets. Mercury, Venus, Earth, and Mars. And they're made up mostly like 70% rocks, like silicates, like you can go pick up. And iron, nickel, alloy makes up the other 30% or so, making up the core of the planet that for the Earth is convecting and producing our magnetic field. A little further out, we have the gas giant planets, Jupiter and Saturn. And these are made up mostly of hydrogen and helium by mass. They do contain things like we have on the Earth, rocks and metals, deep in their interior. Jupiter probably has about 10 times the amount that is in the Earth in those elements alone. But they're deep in the interior, and the atmosphere is dominantly hydrogen. Further out, we have the ice giants, and they're fundamentally different than the gas giants. You can see they're a little bit smaller than the gas giants. Their atmospheres, again, are hydrogen and helium-based, but they accreted, they grew in the presence of other materials that formed ices, like nitrogen and methane and ammonia, things that are gases for us, but at those temperatures are in ices. And those compounds make up a significant fraction of the mass of those planets. And for a long time, this was our understanding of how planetary systems should look. We should have small, dense objects in the inner solar system made of rocks and metals. We should have bigger objects in the outer solar system where more volatile compounds can condense into ices. That gives us more mass in solid materials. The objects can grow faster and accrete the hydrogen and helium gas of the planetary disk. And that's how we get the gas giants. And then further out, the ice giants form where orbital speeds are slower and more things condense into ices. And so this was our understanding of what a planetary system should look like. Again, small things in the inner system, big things in the outer system. And then in 1995, we found our first exoplanet. This was the pair of astronomers who detected this planet, Didier Queloz and Michel Mayor. They announced their discovery in October of 1995, and they had found this planet. It's called 51 Pegasi b. It's a beautiful name, right? Astronomers name planets after the catalog designation of the star, and then a letter that indicates the planet in the order that it is identified. Uh-oh. Okay. Oh, my screen just died down here. Okay, but why was this so transformational? Well, the planet was not where we thought it should be, and it was not the size that we thought it should be. It's fine now. And the infographic down here in the bottom right is showing us that. So we see the sizes of the planets compared to each other. So 51 Pegasi b is a little bit bigger than the planet Jupiter. So we think in terms of density and composition, it is roughly similar to Jupiter, made mostly of hydrogen and helium. Above that, you can see a comparison of orbital distances for these planets. Now, Jupiter formed at about 5 times the distance of the Earth from the Sun, 5 astronomical units, and it has an orbital period of about 4,000 days. 51 Pegasi b has an orbital period of 4 days. My PhD advisor told me a story about when he had learned about this. So he hadn't been at the workshop where this was announced, but it was big news. And so he heard about it shortly thereafter, and he thought somebody said 400 days. And he was like, no, you can't make a Jupiter at 400 days. That's too close. There's no ice there. It can't grow fast enough. You can't make a Jupiter at 400 days. And then somebody was like, no, Dimitar, we said 4 days. And he said he fell off his chair laughing because he thought it was absurd. You can't make a Jupiter planet at that distance from a star. And he thought it was wrong. And a lot of people thought it was wrong, but it turned out it wasn't. Lots of people went out and confirmed this, and then they found a bunch of other planets very similar to this. And this became sort of the prototype hot Jupiter planet. Very creative names. It is a Jupiter-sized planet that is very hot. And we think now that what happened is our models for planet formation were missing something because we only had one system to compare them to, right? We only had the solar system. And so what we were missing was that planets can migrate through a disk as they're forming. There are torques from density perturbations in the gas disk that can drive inward motion of those gas giant planets. And it turns out, we now think that migration might have occurred in the solar system as the solar system was forming. We didn't think that was necessary before because our solar system is so orderly and neatly arranged. But now we have this new physics and new evidence that this is a very common process. And here's sort of a compilation of, now we're 25 years on from that detection, and here we see a comparison of orbits of the solar system. We have Mercury, Venus, Earth, and Mars in this inner region. Jupiter is here along this dashed line. And all of these other systems, all these little spinning dots, these are all planetary systems that we have found orbiting other stars. None of them look like ours, right? None of them look like ours. They're all very different. And it turned out we were missing some big physics from our models of planet formation. And so now, 25 years on, the field of planet formation has been fundamentally changed by this. We now have detected more than 5,000 planets around other stars. As of this morning, it was 5,557. You have to check every day because it grows. And this is sort of the distribution of planets that we have found. They fall into different classes. We try to classify them sort of by density or composition. And so roughly 30% of them are planets like Jupiter, gas giants. Another 30% or so are planets sort of like our ice giants, like Neptune and Uranus. We haven't found too many terrestrial planets the size of Earth and smaller, things similar to our own inner planets. And that's largely a detection bias right now. Those planets are really small and hard to detect. But you'll notice the other pie slice here is about 30%. And this is a class of planets we don't have in the solar system whatsoever. These are planets between the size of Earth and Neptune. Our solar system didn't form one of these planets, and it turns out they're one of the most common kind of planets in our galaxy, and we don't have one. Why is that? Well, it turns out, again, we're missing physics from our models because initially we only had one system to compare to. So planet formation, the field of planet formation is still trying to sort this out. Why don't we have a super Earth in the solar system? And it's leading to new models that we're trying to test against the architecture of exoplanetary systems that we have discovered. This discovery of exoplanets was so fundamental in changing the field of astronomy that in 2019, these two that discovered that first exoplanet, 51 Pegasi b, they were awarded the Nobel Prize in Physics for contributions to our understanding of Earth's place in the cosmos. And so the field of exoplanets occupies now about 20% of the entire workforce in astronomy. It's a field that didn't exist in 1994. Now 20% of all astronomers work on this. And the field of exoplanets has really expanded and brought in interest from many other fields as well, from atmospheric dynamics to mineral physics, people trying to understand these new kinds of planets. And so that brings me to the planets that I'm interested in, the habitable zone planets. What is a habitable zone, just really quickly? So we have sort of limited ability to characterize these planets. And so we have to sort of try to optimize the targets that we go out for and observe. So we have selected planets that we want to look at for habitability based on their orbital periods. In regions where we think, based on models of atmospheres, that liquid water could exist at the surface of a planet. Now, this would produce maybe, potentially, life similar to the planet Earth that we have today. It doesn't guarantee habitability. It doesn't guarantee water. It just means that this might be a good place to look. So the green region in these maps are the habitable zones. These are regions where we think liquid water could exist. For bigger, hotter stars, that is further out. For smaller stars, that's closer in. And most of the good, easily detectable targets we have are around these cooler stars where the planets are closer in. The current number of potentially habitable planets that we have detected so far, amongst that 5,500 odd planets, is around 63. Now, none of these is a direct analog to the Earth. None of them is orbiting a star exactly like the Sun, at exactly the distance of the Earth. But these are all still in that orbital region where maybe they could have liquid water on their surface. And they sort of range different size classes. So some of these are Earth-sized, roughly thinking similar to the Earth in size. But most of them are actually in that super-Earth category where we don't actually know what they're made of or whether they're habitable or not. So there's a lot of work being done on trying to understand that class of planets. The habitable zone also, it moves over time as the star evolves due to the evolution of the star's nucleosynthesis. This is showing the evolution of the habitable zone for a star from the size of the Sun down to the size of our closest neighbor, Proxima Centauri b. You can see the Earth remains in the continuously habitable zone for most of its lifetime, which is great for us, right? And it will stay in that habitable zone for another few billion years. But look at our neighbor, Proxima Centauri, as this GIF loops back around. Initially, it's interior to that habitable zone, right? The inner edge of the habitable zone is set by something we call the runaway greenhouse boundary. This is where we think if a planet had an ocean of water at its surface, it would be receiving so much stellar radiation from its host star, it would be so hot on the surface, it would be hot enough to evaporate that whole ocean. So we think if this planet had an ocean early in its lifetime, it would have all been vaporized and in the atmosphere. And the question is, can that ocean survive so that this planet could become habitable later in its lifetime? One issue with that, of course, is that stars are very active, and the closer you are to your star, the more damaging stellar radiation you receive. There are flares, there are coronal mass ejections, like I just showed you in that diagram. And what can happen is they photolyze the upper atmosphere, and they can drive escape. They heat the upper atmosphere, it becomes more poorly bound, and it can flow away. So if we have an ocean of water and we evaporate it into our atmosphere, potentially we can lose that ocean before we even get into that habitable state, depending on how long that time period lasts. So we want to test this idea for some of our closest exoplanets that are rocky, that could have started off with an ocean of water. Our closest, best current targets was a planetary system detected in 2017 called the TRAPPIST-1 system. This is a system of 7 planets, and here you can see a comparison with the inner solar system and with Jupiter's moons. This star is very small. It's almost the size of Jupiter itself. And so the planets have to be very, very close to that star to be habitable. They are all roughly the size of Earth, meaning maybe they have roughly the composition of Earth, but we don't know until we can test their atmospheres. So right now, our current best instrument to actually observe the atmospheres of exoplanets is the James Webb Space Telescope, which launched into space 2 years ago on Christmas Eve, and it's taken science observations for the last year and a half. And I was fortunate enough to be on a team selected to take observations of one of these inner planets, the TRAPPIST-1c planet. Now, in the system, E, F, and G are in what we call the habitable zone, so TRAPPIST-1c is more of a Venus analog. But we're going to push inward with these observations as James Webb as we have a better understanding of the instruments on James Webb. So first, we're going to test our models and our observations on this planet. And our models actually predict that this planet actually should have an atmosphere. It should probably not have any water left in its atmosphere, but it could have a residual atmosphere of oxygen that was derived from that water originally. So we're looking here at different initial water abundances from sort of a little less than the Earth's current oceans to 100 times more, and looking at a range of different stellar radiation. And we find that this planet, from our models, should have an atmosphere about maybe a hundredth less than the Earth, up to 100 times more. And what we found was that we were trying to use these observations called eclipses, where the planet itself goes behind the star. And we're looking at loss of the light of the planet, and that gives us sort of a measurement of the temperature and a little bit of information about the atmosphere of that planet. And we got those observations in February of this year, and this was then published in Nature. And we got one data point to compare against our models of this planet's atmosphere. And what we can say for sure is that it doesn't have an atmosphere like Venus. It is definitely not Venus. We were looking in particular at a wavelength where carbon dioxide would absorb very strongly. And we didn't see very strong carbon dioxide absorption, but it could be consistent with an atmosphere. We see the sort of purplish and reddish models are both relatively consistent with this. These are thin atmospheres of sort of oxygen plus some carbon, a little bit of carbon dioxide. So a relatively Earth-like atmosphere, although a very un-Earth-like planet. So in the future, we will be able to take observations of more of these planets, more habitable planets. And here's sort of a cartoon of what our stellar neighborhood looks like in terms of the planets available to do these kinds of observations. And so in the future, we will be able to test models of habitability, of climate, of atmospheric chemistry, and planet evolution by looking at these planets that occupy all sorts of different time periods, ages, compositions, stellar radiation, and all the parameters you might want to test about a planet. My colleague, Mathieu Lepatre, gave a talk last year at the Faculty Forum where he posed planets as experiments, as full-scale experiments. And so you cannot think of a grander experiment than using exoplanets as experiments to test your models on. So I sort of challenge you guys to think about how can you use, if you had a sample of 10 planets that are Earth, but not quite Earth, what could you learn about your models? What pieces of physics are missing from your climate models that you might learn by looking at another planet that's Earth but not the Earth? So I'll stop there.